I know they're a little small, but we've got 4 equations written up here. Step 1, I want you to tell me what type. So identify the type of reaction. Okay. After you've identified the type, predict the products. Okay, and I'm going to add if necessary. Okay, because remember, not all reactions are you required to predict the products of. Once you've got your products predicted, go ahead and balance the equation. This is something we will work through together, but you need to get started on it. Start putting some of those pieces down. And as far as the recording goes, I'm going to pause while we work on it. So if we go through and address the first question, we want to identify the type. So in identifying the type, what I would recommend you fall back to is the summary slide that talks about the patterns that we can find within our chemical reactions. Okay, that's where we have A's and B's. One of them is red, one of them is blue. Vaguely sound familiar? And if that doesn't, you need to go back and do 2 things. 1, download the slideshow that you have access to. It is at the very first link, and every single module is a review page, and that review page has the slides linked in it. Okay? And then 2, you should actually watch the lectures, because the lectures talk through those slides. Okay, so you should do that. So if you're missing that information, that's because you're not doing what you agreed to do when you signed up for the class. Okay? So in identifying the type, if we start with that first question, what we're trying to do is look to see how that matches our patterns. So first and foremost, it starts with 2 things. Because it starts with 2 things, we immediately know what reaction this is not. Because one of our reaction types starts with 1 thing. What reaction type starts with 1 thing? Single displacement or single replacement reactions do not start with 1 thing. Decomposition. Decomposition starts with 1 thing and it turns into multiple. Okay? So for those people that were referencing the replacement styles, okay, what you were starting to reference is how many things were in each of those pieces. That's a secondary question. What I asked was how many things are there? There is 1 thing and 2 things separated by the mathematical operator of that plus. Okay? Because I have 2 things, I know decomposition is off the table. Okay? I can use that argument for every single one of these, okay, because they will all start with 2 things. The third one gets a little bit more challenging because it's in the English language and we'd have to do some interpretation, but decomposition is still off the table. Okay? Combustion start with 2 things. Single replacement start with 2 things. Double replacement starts with 2 things. Neutralization starts with 2 things. And there's another reaction type that's not on the list. Combination reactions start with 2 things. Okay? So more than likely, the reactions you're going to look at will start with 2 things. Okay? At least, because the majority of our chemical reactions start with 2 things. Kind of, sort of? Okay. So how do we differentiate after that? Okay, this is where those people were starting to kind of break down what's happening in each of those formulas. Okay? And hopefully what they were seeing, admittedly they said it kind of wrong to begin with, is that we have Au, which happens to be gold, which happens to be a metal, and then we have NO3, which is a really complex looking thing, but all of those complex looking things happen to be a nonmetal. So we're looking at a metal and a nonmetal, okay? And it is a complex ion. Okay, we move to the next one. We have a metal, and then we get this weird, goofy looking thing again, which is another complex ion. Okay? It's not really a nonmetal, it's a complex ion. So calling it a nonmetal is a little bit weird, but it is at least an ion. Okay? If we push back to it, what charges do all of our metals have? All of our metals are positive. They're all cations. What's the charge on NO3? Negative. That's an anion. Our potassium metal is a cation. The chromate is an anion. So we're looking at taking two ionic species and reacting them with each other. Those two ionic species each have two components. Okay? So if I'm going to run a chemical reaction here, it doesn't really make sense as far as the patterns, or really looking at the patterns. There's really only two reactions that fit the patterns. That's going to be my double replacement and my neutralization. How do I differentiate neutralization from double replacement? Neutralization has an acid. Okay, I love it, except none of those say acid. So you have to be able to look at the formula to interpret what an acid is, and what you started to then mouth after that. We have an H in front of our formula, followed by our anion, and then we should see the aqueous in back. That's not happening in that first question. First question? It's a me, a Mario. It's not happening in the first question, so it's not a neutralization. It's going to be a double replacement. Make sense? What happens with the next one? I see a metal again, aluminum. So I might go, ooh, that's another cation anion. But what's the metal connected to? Maybe like it's connected to a solid. What does that S stand for? Solid. It's saying that that is aluminum by itself. Is it connected to anything? No, it's all by itself. Okay? It's the element in its elemental state chilling by itself. Okay? That should be a giant red flag for single replacement. So this was double replacement. This one is our single replacement. Okay? We could continue to manipulate that and see how it matched the pattern. We have cation anion. Okay? Officially, our aluminum is not a cation. It's a metal. And we go through and run that single replacement reaction. The metal and the cation swap places. Why would the metal and the cation swap places and not the metal and the anion? What charge do our metals become in compounds? Positive. That's why it's swapping with the cation. Okay? So if we understand those basic principles to go back to our common ionic charges, it helps us to manipulate those systems. We have propane reacts with oxygen gas. We could get a little bit fancier, C3H8 plus O2. Okay, and you'll note I didn't specify any of the phases. I'm lazy and I don't specify the phases. Okay, generally speaking, you don't have to either unless you're specifically being asked to do so. Okay, so C3H8 plus O2. Okay, I have two things again, but all my reactions had two things. This doesn't match the single replacement reaction. Okay, it doesn't match the double replacement. Neutralization required an H in front and an AQ in back. Might be important if I had phases then. Okay, but I definitely don't have an H in front. So it's not neutralization, double replacement, single replacement. It's not decomposition, which means it's combustion. Are you required to know what combustion is? Yes. Okay. Mostly because it's something you already have broad experience with. Okay. That's probably how you got to campus today. It's actually what you're doing literally right now. Just you existing is a combustion reaction. Okay. We move to the next one. That says combustion. What's the last one show? We have that metal, cation, anion. That's fitting our single replacement reaction. We're, again, looking at a single replacement reaction. SR would have been faster to write. We good? Everybody understand how to label those? All right. I want to point out something that one of your classmates noted that I thought was kind of an important observation, is that they went through and they looked at it and they struggled to figure out, I think, one of the reactions. Okay? And what they had gone through and done is they said, well, I'd already done double replacement, I've already done single replacement, decomposition didn't fit, okay? So it must be neutralization or combustion. Okay? What you're assuming in that statement is that I've given you exactly the exact one-for-one match for all of the things that were listed. That's test-taking strategy. I'm aware of test-taking strategy, and I break those patterns. Okay? Which means I could give you 5 reactions that were all single replacement. Perfectly acceptable. Okay? So just because an answer choice has been used does not mean you can't use it again. Does that make sense? So be careful trying to eliminate answers in that respect, because it can be a dodgy practice. It is an okay practice, you just have to realize be careful with it. Right? When should you fall back on test-taking strategy? When you don't know the content, then fine, do whatever test-taking strategy you got. Okay? But if you know the content, freaking use your brain, prove the content knowledge, not how to take a test. Okay? So we've identified the type. We're all good with the types? Cool, which then moves us to predicting the products. Okay? When it says predict the products, there's an interesting caveat. It also says, if necessary. Are you required to predict the products for all of our chemical reactions? No. And if you're like, I don't know that answer, you should probably go back and rewatch the lecture videos, because the lecture videos very clearly state that you're not responsible for for some of our chemical reactions. The ones you're not responsible for, your decomposition and your combination reactions. You're responsible for combustion, you're responsible for single replacement, double replacement, and neutralization. Okay? Why not for the decomposition and the combinations? Those involve a little bit more chemical thought than you have the knowledge base to deal with. Okay? Could you do it? Sure. 151, go for it. But in 130, we don't need you to push to that level of content, so don't stress about it. Make sense? Okay. But to that end, all of these were double replacement, combination, or single replacement, which means you need to be able to predict the products for every single one of these reactions. Hooray! Okay? That's going to... Oh, son of a horse. Don't make fun of my language. Stupid chair. Oh, I got to get rid of a bunch of stuff so that we can actually write this out, because this is going to start to take up some space. Okay? So, we're going to delete all those, and we'll go back up to that first equation. Delete all those. And now we want to kind of process through that one. Okay? When we're exchanging the double replacement, okay, it's one ion in, one ion out. Okay? But at the same time, it's pairing up again. Okay? So I can exchange these two things for each other. By putting this first C into that compound and kicking this one out, that's a single replacement. But because I'm putting that C back into a new compound, that's what makes it a double replacement. Kind of, sort of? And when we see the single replacement, we'll talk about that. And of course, I drew my arrows over the top of everything. Memorize, memorize, memorize. Okay. So we had gold nitrate, potassium chromate. Okay. If we're going to go through and do our double replacement, we want to swap those species around. Okay? It does not matter which ones you decide to, it doesn't matter if you decide to swap the anions or the cations. Okay? So the order in which they appear does not matter, okay? But it does matter that you've done that swap. So I can write K with my NO3 and gold with my chromate. I'm going to come back to that in a second. Or I could be writing AuCrO4 plus KNO3. Does that make sense? Orders completely identical, doesn't matter. We good? Okay. Now we want to go back and talk about some of the details behind it. Okay, what do I mean the details behind it? That mouse is going to stay in it. Oh, no, it's not. Cool. Okay. The details behind it have to do with the numbers that move across. Because you'll note, when we look left to right, some of those numbers moved across. Some of them I did not. Okay, so the question becomes why? Okay, well, that why has to do what is the meaning of that number. Okay, so let's look at the very first number we see. What is the meaning of that 3? Three oxygen, true. Say again? Nitrate. Okay. There's three oxygens for one nitrogen to make nitrate. Okay. So that 3 is part of the name or the formula symbol for nitrate. Said another way, I would not do this chemical reaction and say I produced a CrO4. Why? I got rid of the U. The U is part of what makes that gold. That 3, that red 3, is part of what makes that nitrate. Okay? Which means when I transfer it across the equation, it better stay there. Otherwise, I'm not talking about nitrate anymore. And if it changes to NO2, I'm not talking about a double replacement, because I'm now changing the identity of those chemicals, and I'm now moving into a combination or decomposition or some complex variation thereof. Okay? Kind of makes sense? Okay. Since that makes sense, let's go ahead and move to the next number. What is the meaning of that 3? 3 nitrates. Why? To balance gold. That's a different meaning. The 3 was there because that's what made it nitrate. The red 3 was there to balance, to make nitrate. The blue 3 is present to balance gold. So when I go across the chemical equation and I find my nitrate again, should I be moving that blue 3 with it? No, why not? It's not with gold. The only reason I had that blue 3 was to balance gold. It's not with gold, so don't bring the 3 across. Okay? And I don't know about you, but I think that's confusing. We're putting a number in the exact same location, subscript, okay, to the lower right, and that number in the exact same location holds different meaning. That's kind of nasty. Okay? This is why it's so critically important to actually know what your complex ions are, which is why you were told to memorize them and start to work with them. Kind of makes sense? Cool. If I continue through, I have a 2 next to the potassium. What is the meaning of that 2? To balance the charge on the chromate. There is no thing that is K2. That's not a complex ion we worry about. I have potassium ion. I have a 2 there because I need 2 potassium ions to balance the chromate. So when I go across the reaction and find my potassium, my K, is it with chromate? No, which means 2 doesn't move. We continue through. We move to the 4 in CrO4. This one's a bit of a screwball because are you required to memorize CrO4? Really? Were you? I didn't think you were. So you saying yes, I was like, I don't think chromate was one I told you you needed to have memorized. It's one that I told you you need to work with. Okay? And if you don't know it, that's fine. You look it up. Okay? But on an exam, you're not required to know that. Okay? We're modifying the exam in this case, so you didn't need to know the identity of chromate for the initial question that was asked. Make sense? Okay? That 4 means I have 4 oxygens to balance the chromium in the compound chromate. Okay? So if I'm going to have chromate, I need the 4. It's part of the identity of that polyatomic ion, which means the 4 must travel with it. Kind of, sort of? Cool. Have we predicted the products? I just realized I'm going to have to deal with phases probably. Okay, did we predict our products? Sort of. Okay, we did the double replacement, so we now have those products there, but are our products actually correct products? No, we still need to balance them, and this is where I like that wording and I don't like it at the same time. Okay? When you say balance, are you saying balance the equation?
Yeah, you got to do the thing with the letters and the numbers on the side and the whole thing.
Cool, that's why I wanted clarity. No. I do not balance the equation yet. I need to make sure my formulas are balanced. So before we start moving into balancing the chemical equation, I have to ensure that the formula for KNO3 for potassium with nitrate is an appropriate formula. Is that formula internally balanced? To figure that out, I have to know the charges on those things. Am I required to know the charge on potassium? Yep. What's its charge? A +1. What's the charge on nitrate? -1. So how many potassiums and how many nitrates do I need? 1 of each. My formula is correct for my potassium nitrate. Okay? Small thing on notations, you'll note that when I go through to balance a formula, I write all the charges underneath. Because if you start writing the charges up above, the problem with that is you're now incorporating a charge into your chemical formula. It's not there. Okay, you aren't showing it to explain the charge of the chemical formula. You're showing it to show the charge on the individual ion, but you're writing it into the formula. It now becomes confusing, and I know multiple instructors that refuse to accept credit for that. Okay? So you need to be real careful with where you're showing your work. If you're going to show your work like that, then that's fine. You rewrite your whole flipping equation again, and you do KNO3 without those charges. Make sense? Okay. So potassium nitrate was fine. What's the next deal? We have gold and chromate. Are you required to know the charge on gold? No. Are you required to know the charge on chromate?
Yes, -2. No.
Were you required to memorize chromate? No. So do we know the charge on chromate? No, because if you don't even know what chromate is, you're not expected to know what its charge is. Okay? So if I don't know the charge on either of those species, how could I possibly correctly predict the proper formula?
You look at the other side.
I go back to the other side where I was given correct formulas, and I can evaluate from there. What is the charge on potassium? A +1. There are 2 potassiums there. Okay? I have 1 chromate. What must its charge be so that I get an overall charge, upper right-hand corner, of 0? It has to be a -2. Okay? So the chromate is a -2. I can go back over here. It's a -2. What do I do for gold? Am I required to know the charge on nitrate? Yep, that's one I'm required to memorize. That's a -1. There's 3 of them. Overall charge must equal 0, upper right-hand corner, plus there's 1 gold times an unknown charge. I get x minus 3 equals 0, and x equals +3. The charge on my gold is a positive 3. Is that the proper formula for gold chromate? No. Because those charges don't balance. Based off of nomenclature, you remember the nomenclature rules where I showed a formula to deal with how to balance out all those charges? Yeah. Ta-da! If you were doing that process in nomenclature, this now becomes easier. If instead you were doing something else, you got to learn a new process. Sucks for you. Okay? This is why I'm scaffolding the things the way they're scaffolded. It's not just random thought most of the time. Okay? What's the lowest common multiple between 3 and 2? 6. How do I make a 3 into a 6? I need 2 golds. How do I make a 2 into a 6? I need 3 chromates. Ooh, that looks like 43. I need parentheses. Okay? Now I've predicted products. Are there any extra things I need to worry about that, full disclosure, I don't have enough stuff memorized to actually be able to answer appropriately, but we'll stumble through it together? Is there anything else I need to worry about when predicting products of a double replacement reaction? Yes.
Their state, solid, liquid, gas.
Their physical state. You mean that thing that I was like, I don't want to worry about, so I'm going to leave it off the equation? Yes. Okay? So if we went back and looked at the question, I'm pretty sure, though not positive, these were aqueous. Okay? So we are required to specify the state for our 2 predicted products. How do we figure out the state? It's Arizona, Mike. Sorry. You can boo that. That's fine. Or not. Okay. How do I figure out their physical state? It's a requirement for all double replacement reactions. What do I have to do?
Check the solubility rules.
Somebody just saved you from playing games. Check your solubility rules. So you'd go and look at the solubility rules, and now you have to manipulate and understand what's going on within the solubility rules. Okay? If you look at the front of the exam, guess what's on the front of the exam? Solubility rules. Which solubility rules? The solubility rules that are necessary, plus some distractors, to answer a question or multiple questions within the exam. Okay? If you look at the front of this, are you going to be able to find the solubility rule that explains what's going on with this? You'll get one of them. I doubt you'll get the other one, but I could be wrong. Okay? Because I don't want to give you 30 solubility rules. I only want to give you a couple that are relevant. Can you prove to me you understand how to manipulate and use them? Fine. That's all I need to see. Okay? Yes?
Is it for double replacement, are we finding whether it's like a reduction or oxidation?
Nope. There's no reduction or oxidation, but conveniently within the questions that we picked, we'll bring that back up. Okay? So, solubility rules. There's 2 solubility rules that I tell you I think you should memorize so you never have to worry about because they get you information pretty quickly. Okay? The 2 rules are... Okay, cool. No one listened to me. That's fine. Okay? Yet, right? You're working on it. Group 1 metals are always soluble. So group 1, anything in that first column. I see K in that first column, which means the phase for KNO3 is soluble, which means I write S. No, because S means ooh, wow, nice chorus. So what do we write for soluble? AQ. AQ for it's dissolved in water. Okay? I would then go through, what's the second rule you should memorize? No Nope, not the insolubles. Nitrate. Nitrate is always soluble. Why memorize those? Because they are always true. They will always be soluble. Why not memorize anything else? Well, if you carefully go through and look at all the other ones, guess what you'll find? They all have exceptions. Okay, so you can't just memorize a rule and be always correct. You're going to end up finding you have to memorize an exception to said rule. Okay, that's why I don't bother to memorize those. Okay, so at this point, what we would do is go into our table, hope we could find either gold, AU, or chromate. Is it in the front?
Yeah.
Is it really?
Chromate's number 2.
Oh, cool. So what was the rule?
Always insoluble is chromate.
Always insoluble, and if it's insoluble, it doesn't dissolve, which means it stays solid. But you said it's always insoluble?
Except when rule 1.
Okay, there we go. There's the exception. Except where Rule 1 and 3 apply, or Rule 1, something like that. Okay, make sense? Which means we now have the phases. Are we now done? For the love of God, what do we have to work on now? Now we have to balance the overall equation. Whoop, wrong eraser. So now we would navigate the entire process. Okay, gold on the left. 1, thank you, on the right. 2, it's not balanced, so I need a 2 in front. Nitrate on the left, because quite frankly, I'm sorry, I don't care about your opinion. I'm not balancing it by elements. Okay, you want to balance it by elements, go ahead, but I'm balancing it complex ions. Nitrate on the left, 3 on the right. I only have 1. It needs to become a 3, so what do I need? A coefficient 3 in front. Potassium on the left. 2, potassium on the right. 3, we've got the coefficient that we've changed. Okay. Do those balance? Nope. So again, I need to come up with a number that allows them to balance. Okay. What number is going to allow 2 and 3 to balance? 6. What's your statement?
I was going to say, what are the 9, 3, 6 on the left, since it has a 2 coefficient?
Good catch. I didn't see that. Yep. Good catch. I missed it. Screw potassium. We're going backwards. My bad. Nitrate, we have the 3 on the left and the 2 that comes in front. So we have, thank you, 6 nitrates. How many nitrates do we have on the right? 3 or 1, depending on your opinion. We brought the 3 in so that it balanced. Okay, so if it starts at 1, what do we need to do? Make it a 6 by putting a 6 in front. Everybody track that? Okay. I want to lean into that a little bit. What did you all just discover? That was a kind way of saying it. It's easy to make mistakes. I made a mistake. It happens. Okay? If we went through and continued to balance this out, I would very likely get caught in a loop, constantly changing numbers. And I'd be like, what the hell did I do? And then eventually I would be able to come back to, oh yeah, I forgot to deal with that number. And now all that time that I spent in this constant loop, I would have to double back and reiterate. Make sense? So I appreciate you catching the mistake early on. Potassium. I'm now panicked that I made another one. How many potassiums on the left? 2 on the right. 6. How do I make 2 and 6 common? Okay. It's a 6 here, not a 3. Right? I put the coefficient in of 3 so that I had 3 times 2. Yes?
So when you're balancing, do you always start with the elements and polyatomic ions? So you go left to right, so you start with gold, and then nitrate, and then potassium. potassium.
Okay, so there's a good question. When we go through and try and balance this out, does the order in which you balance matter?
It seems like it does.
Hydrogen and oxygen.
Not really. The order actually isn't that big of a deal. There is one caveat to that, and we typically say don't balance hydrogen or oxygen. And that's because they show up in more places. So they become really hard to balance if you start. Like if we tried to balance oxygen right out of the gate, that's going to be a mess because you don't know what coefficient to go through and change. Does that make sense?
Are you able to split up like the nitrogen and oxygen?
You can absolutely split nitrate into nitrogen and oxygen. I said there's no way I was going to do that because that's going to mean I got a million oxygens I got to balance later on, and I don't want to do that. So if that's something you want to do, yes, you can do that. I will sit down with you on your time, and we can do that. But I'm not going to do it in front of the class. I already screwed up nitrate. Like, you're going to throw me elements, I'm going to butcher that horribly. Chromates on the left.
Wow.
Only 3. This 4, I know what you're trying to do. You're trying to multiply it. That 4 was part of the identity of chromate. Okay, that was CrO4. That's not a multiplier. I'm not saying I have multiple of those. That's part of that one thing. So I only have 3 chromates on the left. How many chromates on the right? Oh, that was neat. Came out at 3. Extra, thanks for catching that. Right? We changed some coefficients, so what could we do? We go back through and we check all of our work. Gold on the left, 2. Gold on the right, 2. Nitrates on the left. I won't screw it up this time. 6. Nitrates on the right. Potassium on the left. Because of that 2. That 2 is different from the 4 in chromate. The 4 in chromate was part of the identity of chromate. The 2 next to the potassium isn't an identity of potassium. It's the amount of potassium to balance the chromate. Again, you're getting tripped up in that number being in the same place, different meaning. Potassium on the right, chromate on the right, chromate on the left. Which means balanced. And 1 hour later, where are we at? 1 problem down. Okay? And as you freak out and go, oh my God, 1 hour to solve one question. Remember, we talked through it really, really slowly. We looked at each of those pieces and all the way through. In this process, how many different questions were asked? A lot. This wasn't just balance. It was, what chemical reaction was it? There's a question. Predict the products. There's a question. Balance your products. There's a question. What's the phase of your products? There's a question. We didn't solve one question. We solved 6 or 7 questions easily. Does that make sense? We feeling okay with that one? Okay, let's move to one that brings in Eden's question. I'm gonna trying to pick the best way to do this, and I don't really know the best way. According to my timer, it's not an hour later. It's only 38 minutes. Aluminum, cadmium acetate. It's not going to bite me this time, but I'm going to go ahead and do the phases. It sort of bites me. We said it was a single replacement reaction. We want to go through and do the single replacement. Okay, the single replacement is that we're putting one metal in, one metal out. Okay, if we put one metal in, one metal out and in, then we'd be doing a double replacement. Okay, so as I swap this out, my products are going to become, cadmium plus, where did it go? I already forgot my formula. Aluminum with the acetate, which is getting kind of crunched. I'll move it here in just a second. Well, that did not work as elegantly as I thought it would. Really at all. At least it sort of fits in there. We good? Okay. Why did I not write 2 acetates? Okay. The 2 on our reactant side was to balance out the cadmium. Since I'm not with the cadmium anymore, that 2 does not transfer. Okay. The 2 next to the carbon. Why is the 2 transfer with the carbon? That's part of what makes it acetate. I have to have that in there. Kind of make sense? Okay. Have we predicted our products? No. No. Why have we not predicted our products? We need to ensure that the products that we've predicted are correct first. Do we have proper formulas? Okay. The cadmium is just chilling by itself. We're going to come back to that one in a little bit, but it should swap out and look exactly the same as what the aluminum was initially. If we go through and look at our product with the aluminum and the acetate, what's the charge on aluminum? +3. Are you required to have that memorized? Yes. What's the charge on acetate? -1. Are you required to have that memorized? Yes. Is that formula balanced? No. How do I balance it?
Put parentheses around acetate and add.
I need 3 acetates to balance the aluminum. Make sense? Okay. Now I've got products mostly predicted, but there's still some issues. What's the last part that I have to deal with? Our phases. Okay, and recognizing what's going on with the phases for these. This isn't solubility rules per se. It could show up with the salt, which I'll elaborate on in a second. Okay, but the biggest thing that you really need to kind of zoom in on is that when you look at the metals, okay, the metals are going to change their quote-unquote charge. And this is where, yes, we are going to bring in oxidation state, but we'll call it charge for the moment. Okay? The cadmium that we predicted as our product is going to look just like the aluminum on the reactant side, which means its charge is 0. And its phase will be solid. Okay? How do I know its charge is 0? Not because it's by itself.
There's no charge specified there.
Elaborate. Yes, there's no charge specified, but where?
In the upper right hand.
There we go. Upper right-hand corner, there's no charge specified. If we look at the cadmium in our reactant, is it charged? Yes. That cadmium is actually a +2. Okay? So interestingly, our quote-unquote charge changes in the course of a single replacement reaction. Okay? Again, we'll come back to that in a little bit. This is our basic pattern behind it. How about for the aluminum acetate? What should its phase be? One of the other fun rules that's good to have memorized, acetates are always soluble. That's going to come out as aqueous. Okay? Kind of, sort of? Okay, so you do kind of pull in the solubility rules, but you're pulling it in for the salts, which is a metal and non-metal species. Any of the ionic compounds are typically called salts. So far, so good? Questions about any of it? What was next? We got our products. Balance. Did we balance it? How do we balance? Aluminum. How many aluminums? 1 and 1. So that looks balanced. How many cadmiums? 1 and 1. How many acetates? 2 and 2. So is it balanced? On my screen, it wasn't there. 2 and 3, which means our acetates are not balanced, so we should probably go through and balance it. It's not Friday yet, is it? Okay, what's the common multiple between 2 and 3? So how do I make the acetate on the product, a reactant side, a 6? Try again. Try again. Put a 3 because we have a 2 there. And Willita, you may have been talking about the product side. If we go to the product side, how do I make a 3 into a 6? I need a 2 in front. Okay? We change the coefficients, which means how many aluminums? 1 and 2. How do we fix? The one on the left needs to become a 2. How many cadmiums on the left? 3. How many cadmiums on the right? 1. So what do? Stupid computer, get out of the way. Put a 3. How many acetates? 6 and 6. I changed coefficients, so what should I do? So we would check it again, and we find out that hopefully it balanced it. Oh my God. Okay. So, for the record, before you take the exam, make sure you eat some good food and get some good sleep before you take a test. Ideally before you lecture too, but there's only so much you can do. Make sense?
So you said the first solubility rule is group 1 metals are always soluble. What did you say the second rule is?
So the exact order behind them is a little bit off. I usually go group 1 metals are always soluble, then I say acetate is always soluble, and then I say nitrate is always soluble. Okay. The number that they're called is rather arbitrary. It doesn't really matter.
Thank you.
Okay. Insult to injury, the solubility table that you see is not even close to all the solubility rules. You're getting a very, very small portion. Okay. So cool. Are we done? No. How much more time? 15 minutes? Okay. Focus. What was Eden's question? Eden was asking about reduction and oxidation. Okay. Reduction and oxidation take the stuff that we're looking at and they start to repackage things because of a rather simple observation that we actually already made for this case. When we look at the cadmium, what quote-unquote charge did it start at? It started at a +2 because we know the acetate was a -1. There's 2 acetates. So for that formula to be correct, the cadmium has to be a +2. Right? And one of the kind of statements is when we went through and looked at the product for that cadmium, I said, you just do this. Okay? And when we just do this, it has a charge of 0. So if we're looking at, again, quote-unquote charge, the cadmium changed its charge. How do we change charge? Okay.
By itself, it's supposed to be like in the free state, so then it's 0, right? Right?
Yes and no. Okay. It's still going to come back to what happened. How did this happen? Okay. It's just cadmium, theoretically, by itself. Okay. Well, what makes it cadmium? How do I know I'm looking at cadmium? The protons, the neutrons, and the electrons. The protons define the element. So for cadmium, 29 protons. Right? Hopefully I read the right number that time. Okay. The neutrons, okay, the neutrons define the mass. So with protons and neutrons, I get its mass. The average mass for cadmium is going to come in, I said 29. Fuck. Cadmium is 48 protons. I'm so done. The number of neutrons with the number of protons get us our average mass, which is 112. 112. Okay. What gets us our charge? It's the balance of our protons and electrons. Since I can't change the number of protons, if I'm going to change the charge from a +2 to a 0, I have to change the number of electrons. And I'm already palpitating, freaking out about this, because the issue with electrons is they're negatively charged. So I've got a minus sign that I've got to make sure I don't fuck up when I deal with manipulating this charge.
So it lost 2 electrons.
Okay, thank you. Help me out. Okay, we had to lose 2 electrons to go from a +2 to a 0. What does loss mean? What does loss mean? Negative. If the electrons are negatively charged, what am I doing? I'm making it more positive. To go from a +2 to a 0, thank you for making the mistake for me. I was going to do it too. Okay? We didn't lose electrons. We gained electrons. You son of a horse. Can you just... I need something. Just give me something. We had to gain 2 electrons. And your confusion is the exact issue that I was stressing over. Okay, so we have to be real careful when we deal with that, because that transfer of that negative gets really dodgy with what's happening with our numbers. Okay, so we had to gain 2 electrons in that transition. Does that make sense? Okay. Well, where did I get 2 electrons from? Because if we look at the equation, do you see anything about electrons? There's no electrons in the equation. Okay, I heard someone say, oh, it's the acetate. The acetate's doing it. Okay, what was the charge on the acetate? This was a -1. What was the charge on the acetate in the product? A -1, which means how many electrons did it gain or lose? It did not. No electrons were transferred with the acetate. So where did the electrons come from to make cadmium turn from a +2 to a 0? Well, if it's not from the cadmium, but it's not from the acetate, maybe it's from the aluminum. What's the charge for the aluminum? Okay, so we got a lot of +3s. The charge, from where I'm referencing, is the aluminum in the reactant. And we look in the upper right-hand corner, and what do we see? 0. What's its charge? 0. What's the charge on the aluminum in the product? What was the charge on the acetate? The acetate was a -1. There's 3 acetates, which means the aluminum has to be a +3. Which means, what's the aluminum doing? Whoa, just stop multiplying. Nope, don't do that. It's the loss of 3 electrons. Okay? So our single replacement reactions introduce this weird thing of electrons are moving around even though I'm not seeing it in my chemical expression. Okay? So that's where we take a side step out and we say, well, what's going on? How do we figure this out? Because we could start talking about charge, but the charge isn't as explicitly stated, and that's where we shift to the statement of oxidation states. Oxidation state is the balance of protons and electrons. Wait, what was charge? The balance of protons and electrons. So they're the same thing? No. Oxidation state is the balance of protons and electrons on a single atom. Charge is the balance of protons and electrons on anything. Okay? Which could easily just be a unit. So when we're going through and looking at the equation up here, aluminum by itself is a unit. Its charge is always specified in our unit because we see that charge written in the upper right-hand corner. The oxidation state is never specified. And this is where people fight me on it. That's fine. You can fight me on it. I would argue you have to calculate the oxidation state. The oxidation state is now how many times did that atom appear in that unit. So for the blue unit, the circle that we did, how many times do I see the aluminum atom? Once times its oxidation state. There's no other atoms in that unit, which means no other atoms I have to worry about the balance of protons and electrons. Okay? This has to equal then the overall charge. And the overall charge is conveniently written for me in the upper right-hand corner, and it's written as 0, which means when I solve that expression, x equals 0. The oxidation state is trivial. The oxidation state is the same thing as the charge in that unit. But if I switch to a different unit, all things change. And now I have to be a lot more careful about how I approach each of those systems. This is why dealing with that formula system is something that I really push. Always calculate the oxidation state. Always. Okay? Charge is always given to you in the upper right-hand corner. Right? And if you hold those two things true, you're able to reconcile back and forth all of the different systems that we can get to.
Why is it one aluminum and oxygen?
Okay, I was waiting for that. Okay, if we go through and look at it as two aluminums, in this case it's not going to change anything, but what we're referencing is how many in the unit. Why is there a 2 there? To balance the equation. What's the unit? The unit is just aluminum. Okay, so if you decide to incorporate that coefficient, it makes your math a whole lot messier, particularly if we moved into something that was more complicated, like the cadmium acetate. Okay? All we're looking at is the unit, not how many units I need to balance the equation, just the unit. Kind of, sort of? Okay. Does gaining electrons and losing electrons sound fancy? Okay. So we'll say that does not sound very cool, so let's go through and change it. We want to change our language to help make it sound cool. Okay? What is that making it sound cool? Oh, now I got to process all this. Oh, again. Gain of electrons is known as reduction. So when you asked about what's reduction and oxidation, ta-da! Reduction is the process where you have gained 2 electrons. What happened to your oxidation number when you do a reduction? It goes from a 2 to a 0, also known as it was reduced. Oh, neat. It's part of the name. What happens when we talk about loss of 3 electrons or loss of our electrons? This is now oxidation. And when you look at the oxidation number, you can clearly say that it was... No, you can't. Why do we call it oxidation? Has to do with where this was classically discovered. Where this was classically discovered is when we were building boats, okay? Or really any metal object. And we noticed that on exposure to air, they started to change their composition. Okay? What was in the air? Oxygen, and the oxygen was oxidizing our systems. So when we're talking about oxidation, really what we're saying is that if you look at your chemical formula, you're increasing bonds to oxygen. Okay? That's where the oxidation term is coming from. It's a historical term. It does not apply to all chemical reactions. It just applies to those chemical reactions with oxygen. So you got to be a little bit careful about saying, well, did it increase bonds or not? Okay, and even then, deciding whether it increased bonds or not, you would have to know a lot more information about the chemical structures. which you don't know, so don't worry about that. What you're responsible for is being able to label those individual systems. Kind of, sort of? How do you feel? Reduction and oxidation.
Like, I think I was doing it opposite, like the reducer, isn't the reducer what gets like?
You added a whole nother verb conjugation to it that is going to break my brain, but I'll try and work through it a little bit. Yeah, because there is a slide. We've got reduction and oxidation. Okay, so we can say what happened. To the aluminum, it was oxidized. Oops. To the cadmium, it was reduced. Okay, referencing the electrons that were transferred. Okay, if we push on this a little bit further, okay, what made the cadmium get reduced? What provided the electrons to the cadmium? The aluminum. So some smart ass was like, oh, okay, well then that means I can say that aluminum was a reducing agent. Because what did it do? It caused something else to be reduced. Does that mean the aluminum was reduced? No. Okay? It's just a frame of reference on what you're looking at. So there are multiple conjugations of oxidation and reduction. The agent is the one that we'll use. Ant will also show up, the oxidant and the reductant. Okay, I don't think I've ever heard reducer and oxidizer.
I'm sorry, I didn't.
Okay, that's okay, that's okay. No, those are fair conjugations of that word.
Is that gonna be on the test? Like,
The agents, yes.
okay.
So you could be asked a question here, what is the reducing agent?
Aluminum.
Okay, so how do I recommend you figure out the agents? Number one, you process out what happened with your electrons. You figure out what was oxidized and reduced. Okay, and if I'm now looking at the agents, for me personally, it's the opposite of what happened to it. Aluminum was oxidized, that means it was the reducing agent. I already forgot that one. Cadmium was reduced, so it was the oxidizing agent. It caused the aluminum to be oxidized. Okay, is that confusing? Hell yeah, and everybody disagrees, you're wrong. Okay, it is confusing. Shh. Make sense? Enough? Okay. I mean, technically I got a minute. Are you saying I'm done? I appreciate it.